following on in a way from the previous presentation, I'm going to present some work we've done with ATEX with JLR Research. So myself, Alessandro, and my colleague Victor, working together with Simon Robinson and JLR Research. And what we wanted to explore was how we can improve the thermal management strategies for, in this case, a battery-powered electric vehicles. So no internal combustion engine, purely battery and traction motors. So I'm going to go through motivation and objectives we had for the project. I'm going to describe the heat pump we've used for this work, the heat pump concept, and how it's been integrated into the vehicle. Then move on to looking at some cabin and battery warm-up scenarios. So focusing on the warm-up rather than the cooling, as it's the worst case of the two in terms of reducing vehicle range and use of useful electrical energy for driving the vehicle. And then out of all the scenarios that we explore, we're going to select 3 of them. And out of those 3, a favourite to then take on to further work, which also involves building prototypes, physical prototypes. We also look at recirculation strategies for the cabin air. So when we're heating the cabin, we're also losing heat through the glazing, which was a previous study we did, but also through the cabin exhaust. So what benefits do we get from recovering some of that heat that's ejected from the cabin as we pump more hot air into the vehicle cabin? And then some conclusions, and finally future work from this point onwards. So the motivation, as has been mentioned in the previous presentation, is being able to reduce the impact of heating the cabin, but also some of the subsystems, in this case the battery, in this battery electric vehicle. So reducing the detriment in vehicle range that we have by heating these components. Obviously there's other components within the vehicle, so you've got gearboxes, diffs, and so on, but we're focusing for this work on the cabin for the occupant comfort, but also the electrical battery to make sure that we get the best performance out of it. So the objectives for the project were to transfer and redistribute thermal energy, so waste thermal energy from around the vehicle to the areas of the vehicle, to the subsystems of the vehicle that most need that in a cold climate, or particularly a cold climate in this case. We want to minimize the use of PTCs, so positive thermal coefficient heaters. These use electrical energy to heat up elements through which you can flow air, for example, and therefore heat up the cabin. And these are widely used currently to augment the waste heat from other components that can be used for heating up the cabin and vehicle subsystems. To move the heat around the vehicle subsystems, we integrate a dual condenser heat pump, and we analyze how is it best to exchange the heat throughout the vehicle subsystems to minimize the detriment in vehicle range by heating these subsystems. So the heat pump concept is as shown here. So we have compressor, thermal expansion valve, and 2 condensers connected to some liquid fluid loops. On the right-hand side of the diagram, we have a chiller loop. The idea is that we could control the liquids in these 3 loops to specific temperatures, which might be optimal temperatures for warming up or keeping various subsystems in the vehicle at a preferred temperature. So, for example, the hot loop might be used to interact by heat exchangers with the battery or the cabin ventilation system. The medium temperature loop might be used for stabilizing the electric motor temperature, and the low or the chiller loop for cooling the battery, but also cooling the cabin should we need to do this. In terms of integrating that heat pump within the vehicle model, this is a schematic. The main subsystems we're interacting with are ambient, so being able to extract heat from ambient and redistribute it to whichever subsystems need that heat. A heat battery, and this is a non-specific thermal energy storage device. Part of the future work is to figure out what types of thermal energy storage devices might yield the best benefits in this study. And then the motor generator unit, so using the motor generator unit to recover some waste heat, but also in one scenario, for example, chilling it, so using the motor generator unit effectively as a thermal mass that we can store energy in, thermal energy in. On the other side of the diagram, we have the cabin, the battery, and then the PTCs, which are used to provide thermal energy where we can't meet the targets or the objectives we've given ourselves for the cabin and battery warm-up. In terms of how we've modeled this, it's a physical model. What you see in red here, for example, and in blue are electrical and thermal connectors. The subsystems we've considered are the controllers, obviously, to control the routing of the thermal energy throughout the vehicle subsystems. There's a driver model, obviously including a drive cycle. We've got to test the vehicle over some drive cycles. A battery model, so this is an equivalent circuit battery model with varying performance according to temperature and state of charge. A heat battery, so this thermal energy storage device, which in this case is a thermal mass. A cabin model, so this is a downsize in terms of detail cabin model. It's a single zone derived from a 12-zone cabin model used in a previous study, which was correlated to test data. Chassis model, a simple powertrain model, and the heat pump, of course, PTCs, and then also the atmospheric conditions that we're operating within. The idealized heat pump model, and we've idealized it because we do not want to be limited by existing hardware. So there was a rig which was used to test out this dual condenser heat pump system, but we didn't want to be limited by the performance of the system, so reusing the two condensers and the chiller, but also the compressor and the thermal expansion valve from that rig. We wanted to free up the constraints. So we've used some sensible values, for example, for chiller powers, PTC powers, and we've built up this sort of system of heat pumps. So we have the 3 fluid loops down here. Actually, I'll use the slides to demonstrate. Let's start at the top. So we have an array of heat ports. Each heat port connects or interacts with a vehicle subsystem. Immediately below the heat ports, we have 3-way switches, which effectively route the subsystems or connect each of the subsystems to a particular loop in the heat pump. The fluid loops are the ones I showed on a previous slide. So these fluid loops connect, if you like, the 2 condensers and the chiller of the heat pump to a subsystem of choice, and the controllers are what's going to establish or decide which subsystem in the vehicle to connect to which loop connected to the heat pump. So we want to control the temperature of the battery and cabin using minimal electrical power to power the PTCs, but also other components such as the electrical compressor of the heat pump. The heat sources for the experiment are the PTCs, but obviously we want to minimize the use of these PTCs. We want to, or we are able to extract heat from the MGU, so motor generator unit, and reroute it to the cabin and battery. And we've got an extra source of 2 megajoules from the heat battery. And of course, we've got ambient, which we're setting at -5 degrees C for this type of test. The climate duty cycle we're using is this one here, so 30 minutes at 50 kilometers an hour, 30 minutes at 100 kilometers an hour, and then in what a conventional vehicle would be, 30 minutes at idle, in our case, is vehicle stationary, electric vehicle stationary, but we still need to keep that cabin under acceptable temperature conditions for the occupants. So the baseline we're using is warming up the battery and cabin using PTCs only. So this is absolutely the worst case that we're using in this case for the baseline. First scenario is to have a pre-charged heat battery which we can connect directly to the high temperature circuits. In this case, we're not using the heat pump. We're transferring heat from a heat battery to the high temperature circuit. And this is in turn connected to the cabin and battery. Where we can't fulfill the thermal management requirements, we're adding some additional thermal energy using the PTCs. The second or the third scenario is to have a heat battery pre-charged and connected firstly to the high temperature loop. This is with the heat pump actually working. When we cannot extract any more energy from the heat battery, so when the temperature of the high temperature loop and heat battery have stabilized or equalized, we then carry on extracting energy from the heat battery by connecting it to the chiller loop. So we're chilling effectively the heat battery to get it down to a much lower temperature than we would if we just connected it to the high temperature loop. The heat battery for scenario 4 starts pre-charged and connected directly to the chiller loop. In this fifth case, we're connecting this heat battery to both the chiller loop and the high temperature circuit, so we're sort of a double extraction of heat from the heat battery. Scenario 6, we start with a heat battery that's discharged. So the heat battery could have been pre-charged by plugging the vehicle in, or it could have been heat energy recovered from a previous drive cycle. In this case, we're starting with a heat battery completely discharged, so equalized to ambient temperature, and we connect it to the chiller loop to try and bring it down by a small amount of degrees, but still trying to extract some heat from it. Scenario 7, we have a heat battery disconnected from a heat pump. So in this case, we're not using a heat battery. We're using a substitute in a way whereby we're chilling the motor generator unit, extracting thermal energy from the motor generator unit and chilling it down to a low temperature. Finally, scenario 8, we have a heat battery pre-charged. So we're extracting thermal energy from the heat battery. We're also extracting thermal energy from the motor generator unit, and these are both connected to the chiller loop. The heat energy is then transferred by the heat pump to the cabin and battery. PTCs are switched on when we cannot meet the thermal requirements for those subsystems. The 3 scenarios that were selected were 3, 7, and 8. These yielded the largest benefits. These are cumulative benefits versus baseline. This is both traction electrical energy and heating electrical energy considered in this case. So we saw benefits of roughly 12, 13, and 15.5% by the end of the drive cycle by using these scenarios or these thermal management strategies compared to the baseline where we're just using the PTCs. Looking at it from another angle, because those values don't seem to be very large actually, if we just take into account the energy used for heating the components, the benefits start to become a lot more evident and a lot more substantial. And we're still getting the same scenarios coming out with the largest benefits. It's a close call between 3, 4, and 5. So those might need to be reinvestigated further on when we start to specify particular technologies for some of these subsystems. So scenario number 8 is the one that was selected for future work, and the future work we did during this project actually, so now it's past work, was to look at increasing the chiller power from 10 kilowatts to 15, what benefits does that give us? Then having a look at different recirculation strategies. So can we maximize, or to what point can we maximize the recirculation of the cabin air to minimize the amount of waste heat coming out the back of the vehicle? Reducing the amount of cabin air exhaust we're putting out. If we do need to exchange the air in the cabin, how much heat do we need to recover from that exhaust air to be able to see some benefits, useful benefits? So this is our baseline we're starting from, in this case, scenario number 8. So increasing the chiller power, so there's obviously a bottleneck somewhere else in the system because this was only yielding about 0.5% benefit over the baseline. Shifting the cabin recirculation to 100%, there are implications with CO2 build-up in doing this and also moisture, but we'll come on to that later on. We start to see a benefit of around 9%. We then look at a strategy which is more commonly used, starting with 100% and then going down to 60% after 2 minutes of operation, and that was giving benefits of around 7.5% over this baseline. And finally, no recirculation, so we're exchanging all the cabin air as we pump new air in, and the cabin exhaust recovery system was set at 60%. So this experiment, this investigation is, what do we need to do? How much heat do we need to move? How much heat do we need to recover in order to make this viable? After you've established that, you go and see, okay, what sort of hardware specification do we need to be able to arrive to these benefits? So in conclusion, we've rationalized several heat pump coupling scenarios, and we explored or quantified the benefits of reduction of electrical energy consumption for heating, so this would help increase the vehicle range. Possibility of using other subsystems such as a motor generator unit as thermal storage devices or devices from which we can extract additional heat. We're looking into maximizing the benefits using more aggressive cabin air recirculation strategies, and the selection of scenario 8, which could yield, so it's the one that's yielded sufficient benefits to warrant further investigation, which could be or will be at some point to get some hardware designed after we've specified it, and start to do some practical testing to quantify these benefits in an actual real environment. Okay, I'll skip through this since we're short of time, and I've mentioned most of them. Just a 1 point, 100% or aggressive recirculation strategies do warrant investigation into CO2 scrubbing devices, so that we don't get into dangerous situations for the occupants with too high levels of CO2 in their environment. Okay, thanks for your attention. We have a stand here as well, so if you've got other questions, we'll be here obviously this evening as well as tomorrow. Thank you very much.
Okay, thanks Alex. Do we have time for a couple of questions, please? While you're thinking, you've described, Alex, a set of fairly sophisticated thermal management systems, which seem to be getting progressively closer to the perfect system. How close are they to being perfect? You know, how many % off are we?
I'm not sure because we haven't got there yet, so the perfect one hasn't been found yet, but you certainly see diminishing returns.
Yeah.
And
if you think about the old internal combustion engine and 30% of the fuel being wasted as heat, and presumably you're down into single digits.
Well, it's made a big difference. I can't give you a number off the top of my head, unfortunately, but even though the systems are sophisticated and indicate you should be able to arrive to a very, very efficient system, if you can't control that complex routing of heat in this case, you might end up with a system which is in actual fact worse than a simpler system. So look, how you control the device is absolutely key, as is true of how you can control current hybrid electric vehicles. Sometimes the simpler solutions for the level at which we understand how to control these things is better.
Okay, thank you. Okay, one final question. Nice chance. Right, thanks, Alex. That's
okay,
great.
thank you very much.
Okay, do we have